A stock market monitor displays a line graph showing high and low values over time. Figure 14. One regression analysis is used in financial decision-making. Credit. Modification of Stock Exchange by Jacksem/Flickr. CC by 20. Chapter outline. 14. 1 correlation analysis. 14. 2 linear regression analysis. 14. 3 best fit linear model. 14. 4 regression applications in finance. 14. 5 predictions and prediction intervals. 14. 6 use of R statistical analysis tool for regression analysis. Correlation and regression analysis are used extensively in finance applications. Correlation analysis allows the determination of a statistical relationship between two numeric quantities. Regression analysis can be used to predict one quantity based on a second quantity, assuming there is a significant correlation between the two quantities. For example, in finance, we use regression analysis to calculate the beta coefficient of a stock, which represents the volatility of the stock versus overall market volatility, with volatility being a measure of risk. A business may want to establish a correlation between the amount the company spent on advertising versus its recorded sales. If a strong enough correlation is established, then the business manager can predict sales based on the amount spent on advertising for a given time period. Finance professionals often use correlation analysis to predict future trends and mitigate risk in a stock portfolio. For example, if two investments are strongly correlated, an investor might not want to have both investments in a certain portfolio, since the two investments would tend to move in the same directions during up markets or down markets. To diversify a portfolio, an investor might seek investments that are not strongly correlated with one another. Regression analysis can be used to establish a mathematical equation that relates a dependent variable, such as sales, to an independent variable, such as advertising expenditure. In this discussion, the focus will be on analyzing the relationship between one dependent variable and one independent variable, where the relationship can be modeled using a linear equation. This type of analysis is called linear regression. Learning outcomes. By the end of this section, you will be able to calculate a correlation coefficient, interpret a correlation coefficient, test for the significance of a correlation coefficient, calculate a correlation coefficient. In correlation analysis, we study the relationship between bivariate data, which is data collected on two variables where the data values are paired with one another. Correlation is the measure of association between two numeric variables. For example, we may be interested to know if there is a correlation between bond prices and interest rates, or between the age of a car and the value of the car. To investigate the correlation between two numeric quantities, the first step is to create a scatter plot that will graph the x, y ordered pairs. The independent or explanatory quantity is labeled as the x variable, and the dependent or response quantity is labeled as the y variable. For example, we may be interested to know if the price of Nike stock is correlated with the value of the S&P 500, Standard and Poor's 500 stock market index. To investigate this, monthly data can be collected for Nike stock prices and value of the S&P 500 for a period of time, and a scatter plot can be created and examined. A scatter plot, or scatter diagram, is a graphical display intended to show the relationship between two variables. The setup of the scatter plot is that one variable is plotted on the horizontal axis and the other variable is plotted on the vertical axis. Each pair of data values is considered as an x, y point, and the various points are plotted on the diagram. A visual inspection of the plot is then made to detect any patterns or trends on the scatter diagram. Table 14. 1 shows the relationship between the Nike stock price and its S&P value over a one-year time period. To assess linear correlation, the graphical trend of the data points is examined on the scatter plot to determine if a straight line pattern exists. If a linear pattern exists, the correlation may indicate either a positive or a negative correlation. A positive correlation indicates that as the independent variable increases, the dependent variable tends to increase as well. Or, as the independent variable decreases, the dependent variable tends to decrease. The two quantities move in the same direction. A negative correlation indicates that as the independent variable increases, the dependent variable decreases, or as the independent variable decreases, the dependent variable increases. The two quantities move in opposite directions. If there is no relationship or association between the two quantities, where one quantity changing does not affect the other quantity, we conclude that there is no correlation between the two variables. Date S&P 500. Nike. Stock price 4/1/2022 912 4387 18 5/1/2023 044 3198 58 6/1/2023 100 2998 5 7/1/2023 271 1297 61 8/1/2023 500 31 111 89 9/1/2023 363 125 54 10/1/2023 269 96 120 8 11/1/2023 621 63 134 70 12/1/2023 756 07 141 47 1/1/2021 3 714 24 133 59 2/1/2021 3 811 15 134 78 3/1/2021 3 943 34 140 45 3/12/2021 3 943 34 140 45 Table 14 1 Nike stock price and value of S&P 500 over a 1-year time period. Source: Yahoo Finance. From the scatter plot in the Nike stock versus S&P 500 example, see Figure 14. 2. We note that the trend reflects a positive correlation in that as the value of the S&P 500 increases, the price of Nike stock tends to increase as well. A scatter plot showing a positive correlation between the Nike stock price and the value of the S&P 500 over 12 months. As the Nike stock price rises from approximately $87 to $140 per share, the S&P 500 rises from approximately $2,900 to $4,000. Figure 14. 2 Scatter plot of Nike stock price and value of S&P 500 data source, Yahoo Finance. When inspecting a scatter plot, it may be difficult to assess a correlation based on a visual inspection of the graph alone. A more precise assessment of the correlation between the two quantities can be obtained by calculating the numeric correlation coefficient, referred to using the symbol R. The correlation coefficient, which was developed by statistician Carl Pearson in the early 1900s, is a measure of the strength and direction of the correlation between the independent variable x and the dependent variable y. The formula for R is shown below. However, technology, such as Excel or the statistical analysis program R, is typically used to calculate the correlation coefficient. Letter 1D45F equals letter 1D45B sum xy minus sum sine letter 1D465 sum sine letter 1D466 square root letter 1D45B sum letter 1D465 2 minus sum sine letter 1D465 2 square letter 1D45B sum letter 1D466 2 minus sum sine letter 1D466 2. 14. 1. Where n refers to the number of data pairs, and the symbol sum sine letter 1D465 indicates to sum the x values. Table 14. 2 provides a step-by-step procedure on how to calculate the correlation coefficient R. Step representation in symbols. 1. Calculate the sum of the x values. Sum sine letter 1D465. 2. Calculate the sum of the y values. Sum sine letter 1D466. 3. Multiply each x value by the corresponding y value and calculate the sum of these xy products. Sum sine letter 1D465 letter 1D466. 4. Square each x value and then calculate the sum of these squared values. Sum sine letter 1D465 2. 5. Square each y value and then calculate the sum of these squared values. Sum sign letter 1D4662. 6. Determine the value of n, which is the number of data pairs. N. 7. Use these results to then substitute into the formula for the correlation coefficient. R equals letter 1D45b, sum xy minus, sum sign letter 1D465, sum sign letter 1D466, square root letter 1D45b, sum letter 1D465 2 minus, sum sign letter 1D465, 2 square letter 1D45b, sum letter 1D466 2 minus, sum sign letter 1D466 2. Table 14. 2 steps for calculating the correlation coefficient. Note that since R is calculated using sample data, R is considered a sample statistic used to measure the strength of the correlation for the two population variables. Sample data indicates data based on a subset of the entire population. Given the complexity of this calculation, Excel or other software is typically used to calculate the correlation coefficient. The Excel command to calculate the correlation coefficient uses the following format: equals correl A1, A10, B1, B10, where A1, A10 are the cells containing the X values and B1, B10 are the cells containing the Y values. Download the spreadsheet file containing key Chapter 14 Excel exhibits. Interpret a correlation coefficient. Once the value of R is calculated, this measurement provides two indicators for the correlation: the strength of the correlation based on the value of R, the direction of the correlation based on the sign of R. The value of R gives us this information. The value of R is always between -1 and +1, -1 less or equal to R less or equal to 1. The size of the correlation R indicates the strength of the linear relationship between the two variables. Values of R close to -1 or to +1 indicate a stronger linear relationship. If R equals 0, there is no linear relationship between the two variables, no linear correlation. If R equals 1, there is perfect positive correlation. If R equals -1, there is perfect negative correlation. In both of these cases, all the original data points lie on a straight line. The sign of R gives us this information. A positive value of R means that when X increases, Y tends to increase, and when X decreases, Y tends to decrease, positive correlation. A negative value of R means that when X increases, Y tends to decrease, and when X decreases, Y tends to increase, negative correlation. Link to learning. Correlation in finance applications. This video on correlation concepts discusses them with a specific focus on finance applications. The Excel command used to find the value of the correlation coefficient for the Nike stock versus S&P 500 example. Refer back to Table 14. 1 is equals correl B2, B14 C2, C14. In this example, the value of R is calculated by Excel to be R equals 0, 928. Since this is a positive value close to 1, we conclude that the relationship between Nike stock and the value of the S&P 500 over this time period represents a strong positive correlation. The correlation coefficient R can also be determined using the statistical capability on the financial calculator. Step 1 is to enter the data in the calculator, using the data function that is located above the 7 key. Step 2 is to access the statistical results provided by the calculator, using the stat function that is located above the 8 key and scroll to the correlation coefficient results. Follow the steps in Table 14. 3. For calculating the correlation data for the data set of Nike stock price and value of the S&P 500 shown previously. Step description: enter display. 1. Enter data, entry mode second data, X010. 2. Clear any previous data second CLR work, X010. 3. Enter first X value of 2912, 43 2912. 43. Enter X01 equals 2912, 43. 4. Move to next data entry down arrow, Y01 equals 1. 5. Enter first Y value of 87, 1887. 18. Enter Y01 equals 87, 18. 6. Move to next data entry, down arrow X020. 7. Enter second X value of 3044, 31 3044. 31. Enter X02 equals 3044, 31. 8. Move to next data entry down arrow, y02 equals 1. 9 enter second y value of 98. 58 98. 58 enter y02 equals 98. 58. 10 move to next data entry, down arrow x030. 11 continue to enter remaining data values. 12 enter stat, mode second stat. 13 press set until LIN appears second set, lin. 14 move to first statistical result, down arrow, letter 1D45B equals. 13. 15 move to next statistical result, down arrow. X equals 3,480, 86. 16 continue to scroll down until the value of R is displayed, down arrow, letter 1D45F equals 0. 93. Table 14. 3 calculator steps for finding the relationship between Nike stock price and value of S and P 5001. From the statistical results shown on the calculator display, the correlation coefficient R is 0. 93, which indicates that the relationship between Nike stock and the value of the S and P 500 over this time period represents a strong positive correlation. Note: a strong correlation does not suggest that X causes Y or Y causes X. We must remember that correlation does not imply causation. Test a correlation coefficient for significance. The correlation coefficient, R, tells us about the strength and direction of the linear relationship between X and Y. The sample data are used to compute R, the correlation coefficient for the sample. If we had data for the entire population, that is, all measurements of interest, we could find the population correlation coefficient, which is labeled as the Greek letter rho, pronounced rho. But because we have only sample data, we cannot calculate the population correlation coefficient. The sample correlation coefficient, R, is our estimate of the unknown population correlation coefficient. Rho equals population correlation coefficient, unknown. R equals sample correlation coefficient, known, calculated from sample data. An important step in the correlation analysis is to determine if the correlation is significant. By this, we are asking if the correlation is strong enough to allow meaningful predictions for Y based on values of X. One method to test the significance of the correlation is to employ a hypothesis test. The hypothesis test lets us decide whether the value of the population correlation coefficient rho is close to 0 or significantly different from 0. We decide this based on the sample correlation coefficient R and the sample size n. If the test concludes that the correlation coefficient is significantly different from 0, we say that the correlation coefficient is significant. Conclusion: there is sufficient evidence to conclude that there is a significant linear relationship between X and Y variables because the correlation coefficient is significantly different from 0. What the conclusion means: there is a significant linear relationship between the X and Y variables. If the test concludes that the correlation coefficient is not significantly different from 0, it is close to 0, we say that the correlation coefficient is not significant. A hypothesis test can be performed to test if the correlation is significant. A hypothesis test is a statistical method that uses sample data to test a claim regarding the value of a population parameter. In this case, the hypothesis test will be used to test the claim that the population correlation coefficient rho is equal to 0. Use these hypotheses when performing the hypothesis test. Null hypothesis. H0, letter 1D70C equals 0. Alternate hypothesis. Letter 1D70C not equal to 0. The hypotheses can be stated in words as follows. Null hypothesis H0. The population correlation coefficient is not significantly different from 0. There is not a significant linear relationship, correlation, between X and Y in the population. Alternate hypothesis The population correlation coefficient is significantly different from 0. There is a significant linear relationship, correlation, between X and Y in the population. A quick shorthand way to test correlations is the relationship between the sample size and the correlation. If R greater or equal to 2, square root letter 1D45B, then this implies that the correlation between the two variables demonstrates that a linear relationship exists and is statistically significant at approximately the 0.5 level of significance. As the formula indicates, there is an inverse relationship between the sample size and the required correlation for significance of a linear relationship. With only 10 observations, the required correlation for significance is 0. 6325. For 30 observations, the required correlation for significance decreases to 0. 3651. And at 100 observations, the required level is only 0.2000. Note: if R is significant and the scatter plot shows a linear trend, the line can be used to predict the value of Y for values of X that are within the domain of observed X values. If R is not significant or, if the scatter plot does not show a linear trend, the line should not be used for prediction. If R is significant and the scatter plot shows a linear trend, the line may not be appropriate or reliable for prediction outside the domain of observed X values in the data. Think it through, determining if a correlation is significant. Suppose that the chief financial officer, CFO, of a corporation is investigating the correlation between stock prices and unemployment rate over a period of 10 years and finds the correlation coefficient to be 68. There are 10 X, Y data points in the data set. Should the CFO conclude that the correlation is significant for the relationship between stock prices and unemployment rate based on a level of significance of 0? 5. Solution. When using a level of significance of 0. 5. If R greater or equal to 2 square root letter 1d45b. Then this implies that the correlation between the two variables demonstrates a linear relationship that is statistically significant at approximately the 0. 5 level of significance. In this example, we check if minus 0, 68, is greater than or equal to 2 square root letter 1d45b, where n equals 10. Since 2 square root 10 is approximately 0, 632, this indicates that the absolute value of R of minus 0, 68, is greater than 2 square root letter 1d45b, and thus the correlation is deemed as significant. Correlations may be helpful in visualizing the data, but they are not appropriately used to explain a relationship between two variables. Perhaps no single statistic is more misused than the correlation coefficient. Citing correlations between health conditions and everything from place of residence to eye color have the effect of implying a cause and effect relationship. This simply cannot be accomplished with a correlation coefficient. The correlation coefficient is, of course, innocent of this misinterpretation. It is the duty of analysts to use a statistic that is designed to test for cause and effect relationships and to report only those results if they are intending to make such a claim. The problem is that passing this more rigorous test is difficult. Therefore, lazy and/or unscrupulous researchers fall back on correlations when they cannot make their case legitimately. Learning outcomes by the end of this section, you will be able to analyze a regression using the method of least squares and residuals. Test the assumptions for linear regression. Method of least squares and residuals once the correlation coefficient has been calculated and a determination has been made that the correlation is significant. Typically, a regression model is then developed. In this discussion, we will focus on linear regression, where a straight line is used to model the relationship between the two variables. Once a straight line model is developed, this model can then be used to predict the value of the dependent variable for a specific value of the independent variable. Recall from algebra that the equation of a straight line is given by letter 1d466 equals letter 1d45a letter 1d465 plus letter 1d44f14. 2, where m is the slope of the line and b is the y-intercept of the line. The slope measures the steepness of the line, and the y-intercept is that point on the y-axis where the graph crosses or intercepts the y-axis. In linear regression analysis, the equation of the straight line is written in a slightly different way using the model circumflex equals letter 1d44e plus letter 1d44f letter 1d46514. 3 in this format, b is the slope of the line, and a is the y-intercept. The notation circumflex y is called y-hat and is used to indicate a predicted value of the dependent variable y for a certain value of the independent variable x. If a line extends uphill from left to right, the slope is a positive value, and if the line extends downhill from left to right, the slope is a negative value. Refer to Figure 14. 3. Three possible line graphs for the equation y circumflex equals a plus bx, labeled A, B, and C respectively. Graph A shows a line sloping upward to the right if b 0. Graph B shows a horizontal line if b equals 0. Graph C shows a line sloping downward to the right if b 0. Figure 14. Three possible graphs of circumflex y equals letter 1d44e plus letter 1d44f letter 1d465. A, if b 0, the line slopes upward to the right. B, if b equals 0, the line is horizontal. C, if b 0, the line slopes downward to the right. When generating the equation of a line in algebra using y equals letter 1d45a, letter 1d465 plus b, 2x, y points were required to generate the equation. However, in regression analysis, all x, y points in the dataset will be utilized to develop the linear regression model. The first step in any regression analysis is to create the scatter plot. Then proceed to calculate the correlation coefficient R and check this value for significance. If we think that the points show a linear relationship, we would like to draw a line on the scatter plot. This line can be calculated through a process called linear regression. However, we only calculate a regression line if one of the variables helps to explain or predict the other variable. If x is the independent variable and y the dependent variable, then we can use a regression line to predict y for a given value of x as an example of a regression equation. Assume that a correlation exists between the monthly amount spent on advertising and the monthly revenue for a Fortune 500 company. After collecting x, y data for a certain time period, the company determines the regression equation is of the form circumflex y equals 9, 376. 7 plus 61. 8 letter 1d465 14. 4 where x represents the monthly amount spent on advertising in thousands of dollars and circumflex y represents the monthly revenues for the company in thousands of dollars. A scatter plot of the x, y data is shown in Figure 14. 4. A scatter plot helps a Fortune 500 company predict its monthly revenue depending on level of advertising spend. The diagram shows its revenue increasing from approximately $12 million to $19 million, as advertising spend increases from approximately $50,000 to $150,000. Figure 14. 4 scatter plot of revenue versus advertising for a Fortune 500 company. Zeros. The Fortune 500 company would like to predict the monthly revenue if its executives decide to spend $150,000 in advertising next month. To determine the estimate of monthly revenue, let x equals 150 in the regression equation and calculate a corresponding value for circumflex y. Circumflex y equals 9,376. 7 plus 61. 8 letter 1d465 circumflex y equals 9,376. 7 plus 61 8, 150. Circumflex y equals 18,646. 714. 5. This predicted value of y indicates that the anticipated revenue would be $18,646,700, given the advertising spend of $150,000. Notice that from past data, there may have been a month where the company actually did spend $150,000 on advertising, and thus the company may have an actual result for the monthly revenue. This actual, or observed, amount can be compared to the prediction from the linear regression model to calculate a residual. A residual is the difference between an observed y value and the predicted y value obtained from the linear regression equation. As an example, assume that in a previous month, the actual monthly revenue for an advertising spend of $150,000 was $19,200,000, and thus y equals 19,200. The residual for this data point can be calculated as follows. Residual equals observed letter 1d466 value minus predicted y value. Residual equals letter 1d466 minus circumflex y. Residual equals 19,200 minus 18,646. 7 equals 553. 314. 6. Notice that residuals can be positive, negative, or zero. If the observed y value exactly matches the predicted y value, then the residual will be 0. If the observed y value is greater than the predicted y value, then the residual will be a positive value. If the observed y value is less than the predicted y value, then the residual will be a negative value. When formulating the linear regression line of best fit to the points on the scatter plot, the mathematical analysis generates a linear equation where the sum of the squared residuals is minimized. This analysis is referred to as the method of least squares. The result is that the analysis generates a linear equation that is the best fit to the points on the scatter plot, in the sense that the line minimizes the differences between the predicted values and observed values for y. Think it through calculating a residual. Suppose that the chief financial officer of a corporation has created a linear model for the relationship between the company's stock and interest rates. When interest rates are at 5%, the company stock has a value of $94. Using the linear model, when interest rates are at 5%, the model predicts the value of the company stock to be $99. Calculate the residual for this data point. The goal in the regression analysis is to determine the coefficients A and B in the following regression equation. Circumflex y equals letter 1d44e plus letter 1d44f, letter 1d465 14. 8. Once the x, y has been collected, the slope b and y-intercept a can be calculated using the following formulas. B equals letter 1d45b, sum letter 1d465, letter 1d466 minus sum sine letter 1d465, sum sine letter 1d466, minus sum sine letter 1d465 2, A equals sum sine letter 1d466, n minus letter 1d44f, sum sine letter 1d465, n 14. 9, where n refers to the number of data pairs and sum sine letter 1d465 indicates sum of the x values. Notice that the formula for the y-intercept requires the use of the slope result b, and thus the slope should be calculated first and the y-intercept should be calculated second. When making predictions for y, it is always important to plot a scatter diagram first. If the scatter plot indicates that there is a linear relationship between the variables, then it is reasonable to use a best fit line to make predictions for y, given x within the domain of x values in the sample data, but not necessarily for x values outside that domain. Note, computer spreadsheets, statistical software, and many calculators can quickly calculate the best fit line and create the graphs. The calculations tend to be tedious if done by hand. Assumptions for linear regression, testing the significance of the correlation coefficient requires that certain assumptions about the data are satisfied. The premise of this test is that the data are a sample of observed points taken from a larger population. We have not examined the entire population because it is not possible or feasible to do so. We are examining the sample to draw a conclusion about whether the linear relationship that we see between x and y in the sample data provides strong enough evidence that we can conclude that there is a linear relationship between x and y in the population. The regression line equation that we calculate from the sample data gives the best fit line for our particular sample. We want to use this best fit line for the sample as an estimate of the best fit line for the population, figure 14. 5. Examining the scatter plot and testing the significance of the correlation coefficient helps us determine if it is appropriate to do this. These are the assumptions underlying the test of significance. There is a linear relationship in the population that models the average value of y for varying values of x. In other words, the expected value of y for each particular value lies on a straight line in the population. We do not know the equation for the line for the population. Our regression line from the sample is our best estimate of this line in the population. The y values for any particular x value are normally distributed about the line. This implies that there are more y values scattered closer to the line than are scattered farther away. Assumption 1 implies that these normal distributions are centered on the line. The means of these normal distributions of y values lie on the line. The standard deviations of the population y values about the line are equal for each value of x. In other words, each of these normal distributions of y values has the same shape and spread about the line. The residual errors are mutually independent, no pattern. The data are produced from a well-designed, random sample or randomized experiment. 2 diagrams of a best fit line. The first diagram, A, shows a linearly descending line running through the center of 3 vertical sets of scattered points. The second diagram, B, shows a linearly descending line running through the mean of 3 tilted bell curves. The bottom of each bell curve aligns with the position of the 3 vertical scattered points in diagram A figure 14. 5 best fit line, the y-values for each x value are normally distributed about the line with the same standard deviation. For each x value, the mean of the y-values lies on the regression line. More y-values lie near the line than are scattered further away from the line. Learning outcomes by the end of this section, you will be able to calculate the slope and y-intercept for a linear regression model using technology. Interpret and apply the slope and y-intercepts. Calculate the slope and y-intercept for a linear regression model using technology. Once a correlation has been deemed as significant, a best-fit linear regression model is developed. The goal in the regression analysis is to determine the coefficients A and B in the following regression equation. Circumflex y equals letter 1d44e plus letter 1d44f, letter 1d465, 14. 10. The slope b and y-intercept a can be calculated using the following formulas. B equals letter 1d45b, sum letter 1d465, letter 1d466 minus, sum sine letter 1d465. Sum sine letter 1d466 minus, sum sine letter 1d465, 2. A equals sum sine letter 1d466, n minus letter 1d44f, sum sine letter 1d465, n 14. 11. These formulas can be quite cumbersome, especially for a significant number of data pairs, and thus technology is often used, such as Excel, a calculator, R statistical software, etc. Using Excel. To calculate the slope and y-intercept of the linear model, start by entering the x, y data in 2 columns in Excel. Then the Excel commands equals slope and equals intercept can be used to calculate the slope and intercept, respectively. The following data set will be used as an example. The monthly amount spent on advertising and the monthly revenue for a Fortune 500 company for 12 months. Data is shown in Table 14. 4. Month advertising expenditure revenue Jan 4912, 210, Feb 14517. 590, Mar 5713, 215, April 15319, 200 May 9214, 600 Jun 8314, 100 Jul 11717, 100 Og 14218, 400 Sep 6914, 100 Oct 10615, 500 Nov 10916, 300 Dec 12117, 20 Table 14. 4. Revenue versus advertising for Fortune 500 company, zeros. To calculate the slope of the regression model, use the Excel command equals slope, y data range, x data range. It's important to note that this Excel command expects that the y data range is entered first and the x data range is entered second. Since revenue depends on amount spent on advertising, revenue is considered the y variable and amount spent on advertising is considered the x variable. Notice the y data is contained in cells C2 through C13, and the x data is contained in cells B2 through B13. Thus the Excel command for slope would be entered as equals slope, C2, C13, B2, B13. In the same way, the Excel command to calculate the y-intercept of the regression model is equals intercept, y data range, x data range. For the data set shown in the above table, the Excel command would be equals intercept, C2, C13, B2, B13. The results are shown in Figure 14. 6. Where slope B equals 61.8, intercept A equals 9,376. 714. 12. A screenshot of a spreadsheet showing the Excel commands to calculate the slope and intercept of monthly values for advertising expenditure and revenue from January to December. The calculated slope is 61.8 and the calculated intercept is 9,376. 7. Figure 14. 6. Revenue versus advertising for Fortune 500 company, zeros. showing slope and y-intercept calculation in Excel based on this. The regression equation can be written as circumflex y equals letter 1d44e plus letter 1d44f, letter 1d465 circumflex y equals 9. 376, 7 plus 61. 8 letter 1d465 14. 13, where X represents the amount spent on advertising in thousands of dollars, and Y represents the amount of revenue in thousands of dollars. Using a financial calculator, the financial calculator provides the slope and y-intercept for the linear regression model once the X, Y data is inputted into the calculator. Follow the steps in Table 14. 5 for calculating the slope and y-intercept for the data set of amounts spent on advertising and revenue shown previously. Step description: enter display 1 enter data, entry mode 2 ND data, X0. 2 clear any previous data 2 ND CLR work. X0, 3 enter first X value of 4949 enter X0 1 equals 49. 4 move to next data entry down arrow Y0, 1 equals 1, 5 enter first Y value of 12,210, 12,210 enter Y0, 1 equals 12,210. 6 move to next data entry down arrow X0, 20. 7 enter second X value of 145, 145 enter X0 2 equals 145. 8 move to next data entry down arrow Y, 02 equals 19 enter second Y value of 17,590, 17,590 enter. Y, 02 equals 17,590. 10 move to next data entry down arrow X030. 11 continue to enter remaining data values 12 enter stat, mode 2 ND stat 13 press set, until LIN appears 2 ND set. LIN 14, move to first statistical result, down arrow N equals 12. 15, move to next statistical result, down arrow, X equals 103. 58, 16, continue to scroll down until the value of A is displayed, down arrow A equals 9,376. 70, 17, continue to scroll down until the value of B is displayed, down arrow B equals 61. 80, table 14. 5 calculator steps for the slope and y-intercept from the statistical results shown on the calculator display. The slope B is 61. 8 and the y-intercept is 9,367. 7. Based on this, the regression equation can be written as circumflex y equals letter 1d44e plus letter 1d44f, letter 1d465 circumflex y equals 9,376. 7 plus 61. 8 letter 1d465 14. 14 interpret and apply the slope and y-intercept the slope of the line. B describes how changes in the variables are related. It is important to interpret the slope of the line in the context of the situation represented by the data. You should be able to write a sentence interpreting the slope in plain English. Interpretation of the slope of the best fit line tells us how the dependent variable, y, changes for every 1 unit increase in the independent X variable, on average. In the previous example, the linear regression model for the monthly amount spent on advertising and the monthly revenue for a Fortune 500 company for 12 months was generated as follows. Circumflex y equals letter 1d44e plus letter 1d44f, letter 1d465 circumflex y equals 9,376. 7 plus 61. 8 letter 1d465 14. 15, since the slope was determined to be 61.8, the company can interpret this to mean that for every $1,000 spent on advertising, on average, this will result in an increase in revenues of $61,800. The intercept of the regression equation is the corresponding y value when. Interpretation of the intercept of the best fit line, tells us the expected mean value of y in the case where the X variable is equal to 0. However, in many scenarios, it may not make sense to have the X variable equal 0, and in these cases, the intercept does not have any meaning in the context of the problem. In other examples, the X value of 0 is outside the range of the X data that was collected. In this case, we should not assign any interpretation to the y-intercept. In the previous example, the range of data collected for the X variable was from $49 to $153 spent per month on advertising. Since this interval does not include an X value of 0, we would not provide any interpretation for the intercept. Learning outcomes. By the end of this section, you will be able to calculate the regression model for a single independent variable as applied to financial forecasting, extract measures of slope and intercept from regression analysis in financial applications. Regression model for a single independent variable. Regression analysis is used extensively in finance-related applications. Many typical applications involve determining if there is a correlation between various stock market indices, such as the S&P 500, the Dow Jones Industrial Average, DJIA, and the Russell 2000 Index. As an example, suppose we would like to determine if there is a correlation between the Russell 2000 Index and the DJIA. Does the value of the Russell 2000 Index depend on the value of the DJIA? Is it possible to predict the value of the Russell 2000 Index for a certain value of the DJIA? We can explore these questions using regression analysis. Table 14.6 shows a summary of monthly closing prices of the DJIA and the Russell 2000 for a 12-month time period. We consider the DJIA to be the independent variable and the Russell 2000 Index to be the dependent variable. Monthly close DJIA Russell 2001 APRA 2130 4200, 67 2262, 67 1 Mar 2130 2981, 55 2220, 52 1 Feb 21 30932, 37 2201, 5 1 Jan 21 29982, 62 2073, 64 1 Dec 20 606, 48 1974, 86 1 Nov 20 638, 64 1819, 82 1 Oct 20 6501, 60 1538, 48 1 Sep 20 781, 71 507, 69 1 Og 20 430, 5 1561, 88 1 Jul 20 428, 32 1480, 43 1 Jun 20 812, 88 1441, 37 1 May 20 383, 11 1394. 4. Table 14. 6 monthly closing prices of the DJIA and the Russell 2000 for a 12-month time period. Source: Yahoo! Finance. The first step is to create a scatter plot to determine if the data points appear to follow a linear pattern. The scatter plot is shown in Figure 14. 7. The scatter plot clearly shows a linear pattern. The next step is to calculate the correlation coefficient and determine if the correlation is significant. Using the Excel command =correl, the correlation coefficient is calculated to be 0.947. This value of the correlation coefficient is significant using the test for significance referenced earlier in correlation analysis. Using the Excel commands =slope and =intercept, the value of the slope and y-intercept are calculated as 0.11 and -1, 496, 34 respectively when rounded to 2 decimal places. The Excel output is shown below, =correl C3, C14 B3, B14, 0.947 equals slope C3, C14 B3, B14, 0.113 equals intercept C3, C14 B3, B14, minus 1,496, 340, a scatter plot showing a positive correlation between the monthly closing prices of the Russell 2000 and the Dow Jones Industrial Average Stock Index values over 12 months. The diagram shows the Russell 2000 Index rising from approximately 1,400 to over 2,200, as the DJIA increases from approximately 25,000 to over 34,000. Figure 14. 7 scatter plot for monthly closing prices of the DJIA versus the Russell 2000 for a 12-month time period. Data source: Yahoo Finance. Based on these results, the corresponding linear regression model is circumflex y equals letter 1d44e plus letter 1d44f letter 1d465 circumflex y equals -1, 496, 34 plus 0, 11 letter 1d465 14. 16. Assume the DJIA has reached a value of 32,000. Predict the corresponding value of the Russell 2000 index. To determine this, substitute the value of the independent variable, x equals 32,000. This is the given value of the DJIA, and calculate the corresponding value for the dependent variable, which is the predicted value for the Russell 2000 index. Circumflex y equals -1, 496, 34 plus 0, 11, 32,000, circumflex y equals 2023, 66, 14. 17. Thus, the predicted value for the Russell 2000 index is approximately 2024 when the DJIA reached a value of 32,000. Measures of slope and intercept from regression analysis. An important application of regression analysis is to determine the systematic risk for a particular stock, which is referred to as beta. A stock's beta is a measure of the volatility of the stock compared to a benchmark, such as the S&P 500 index. If a stock has more volatility compared to the benchmark, then the stock will have a beta greater than 1. 0. If a stock has less volatility compared to the benchmark, then the stock will have a beta less than 10. Beta can be determined as the slope of the regression line when the stock returns are plotted versus the returns for the benchmark, such as the S&P 500. As an example, consider the calculation for beta of Nike stock, based on monthly returns of Nike stock versus monthly returns for the S&P 500 over the time period from May 2020 to March 2021. The monthly return data is shown in Table 14. 7-date S&P 500 S&P monthly return, percent, Nike stock price, Nike monthly return, percent, 4/1/2020 2,912, 43 NA 87, 18 N a 5/1/2020 3,044, 31/0, 598, 58/0, 13/6 1/2020 3,100, 29/0, 298, 5-0, 1/7 1/2020 3,271, 12/0, 697, 61/0, 8/1/2020 3,500, 31/0, 7/111, 89/0, 15/9 1/2020 3,363, 0, 4/125, 54/0, 12/10 1/2020 3,269, 96-0, 3/120, 8, 4/11 1/2020 3,621, 63/0, 11/134, 70/0, 12/12 1/2020 3,756, 70, 4/141, 47/0, 5/11 2021 3,714, 24, 1/133, 59-0, 6/2 1/2021 3,811, 15/0, 3/134, 78/0, 1/3 2021 3,943, 34/0, 3/140, 45/0, 4/3/12 2021 3,943, 34/00 140, 45/0, Table 14. 7 monthly returns of Nike stock versus monthly returns for the S&P 500. Source: Yahoo Finance. The scatter plot that graphs S&P monthly return versus Nike monthly return is shown in Figure 14. 8. A scatter plot of the monthly return for Nike stock against the monthly return for the S&P 500 index shows a dashed regression line through the scatter points. This is a regression line corresponding to the slope of 0, 83 and the formula y equals 083x plus 02. Figure 14. 8 scatter plot of monthly returns of Nike stock versus monthly returns for the S&P 500. Data source. Yahoo Finance. The slope of the regression line is 0.83, obtained by using the equals slope command in Excel. Equals slope E4, E15C4, C15 equals 0. 830,680,1650. 8. This indicates the value of beta for Nike stock is 0.83, which indicates that Nike stock had lower volatility versus the S&P 500 for the time period of interest. Learning outcomes. By the end of this section, you will be able to calculate predictions for the dependent variable using the regression model. Generate prediction intervals based on a prediction for the dependent variable. Predicting the dependent variable using the regression model. A key aspect of generating the linear regression model is to use the model for predictions, provided the correlation is significant. To generate predictions or forecasts using the linear regression model, substitute the value of the independent variable x in the regression equation and solve the equation for the dependent variable y. In a previous example, the linear regression equation was generated to relate the amount of monthly revenue for a Fortune 500 company to the amount of monthly advertising spend. From the previous example, it was determined that the regression equation can be written as circumflex y equals letter 1d44e plus letter 1d44f, letter 1d465. Circumflex y equals 9, 376, 7 plus 61, 8 letter 1d465, 14, 18, where x represents the amount spent on advertising in thousands of dollars, and y represents the amount of revenue in thousands of dollars. Let's assume the Fortune 500 company would like to predict the monthly revenue for a month, where it plans to spend $80,000 for advertising. To determine the estimate of monthly revenue, let x equals 80 in the regression equation and calculate a corresponding value for y circumflex. Circumflex y equals 9, 376, 7 plus 61, 8 letter 1d465. Circumflex y equals 9, 376, 7 plus 61, 880. Circumflex y equals 14, 320, 70, 14, 19. This predicted value of y indicates that the forecasted revenue would be $14,320,700, assuming an advertising spend of $80,000. Excel can provide this forecasted value directly using the equals forecast command. To use this command, enter the value of the independent variable x, followed by the cell range for the y data and the cell range for the x data, as follows. Equals forecast, x value, range of y data, range of x data. Using this Excel command, the forecasted value for the revenue is $14,320. 52 when the advertising spend is $80 in thousands of dollars. See Figure 14. 9. Note, the discrepancy in the more precise Excel result and the formula result is due to rounding in interim calculations. A screenshot of a spreadsheet showing the Excel forecast command to calculate the forecasted value for revenue. There are 12 rows and 3 columns of data. There is data for the advertising expenditure and revenue for the 12 months of a year, going from January to December. The forecasted revenue value is $14,320,000, when the advertising spend is $80,000. The Excel forecast command for this example is equals forecast open parenthesis 80, C 2:C13, B 2:B13 close parenthesis. Figure 14. 9 revenue versus advertising for Fortune 500 company, zeros, showing forecast command in Excel. A word of caution when predicting values for y. It is generally recommended to only predict values for y using values of x that are in the original range of the data collection. As an example, assume we have developed a linear model to predict the height of male children based on their age. We have collected data for the age range from x equals 3 years old to x equals 10 years old, and we have confirmed that the scatter plot shows a linear trend and that the correlation is significant. It would be erroneous to use this model to predict the height of a 25-year-old male, since x equals 25 is outside the range of the x data, which was from 3 to 10 years old. The reason this is not recommended is that a linear pattern cannot be assumed to continue beyond the X value of 10 years old, unless some data collection has occurred at ages greater than 10 to confirm that the linear pattern is consistent for X values beyond 10 years old. Generating prediction intervals. One important value of an estimated regression equation is its ability to predict the effects on Y of a change in one or more values of the independent variables. The value of this is obvious. Careful policy cannot be made without estimates of the effects that may result. Indeed, it is the desire for particular results that drive the formation of most policy. Regression models can be, and have been, invaluable aids in forming such policies. Remember that point estimates do not carry a particular level of probability or level of confidence because points have no width above which there is an area to measure. There are actually two different approaches to the issue of developing estimates of changes in the independent variable, or variables, on the dependent variable. The first approach wishes to measure the expected mean value of Y from a specific change in the value of X. The second approach to estimate the effect of a specific value of X on Y treats the event as a single experiment. You choose X and multiply it times the coefficient, and that provides a single estimate of Y. Because this approach acts as if there were a single experiment, the variance that exists in the parameter estimate is larger than the variance associated with the expected value approach. The conclusion is that we have two different ways to predict the effect of values of the independent variable, S, on the dependent variable, and thus we have two different intervals. Both are correct answers to the question being asked, but there are two different questions. To avoid confusion, the first case where we are asking for the expected value of the mean of the estimated Y is called a confidence interval. The second case, where we are asking for the estimate of the impact on the dependent variable Y of a single experiment using a value of X, is called the prediction interval. The prediction interval for an individual Y for X equals letter 1D465 letter 1D45D can be calculated as circumflex Y equals plus letter 1D461 letter 1D6FC slash 2 letter 1D460 letter 1D452 square root 1 plus 1 N plus letter 1D465 letter 1D45D minus X 2 letter 1D460 letter 1D465 14 20 where C is the standard deviation of the error term, Sx is the standard deviation of the X variable, and letter 1D461 letter 1D6FC slash 2 is the critical value of the t distribution at the 1 letter 1D6FC. Confidence level. Tabulated values of the t distribution are available in online references such as the Engineering Statistics Handbook. The mathematical computations for prediction intervals are complex, and usually the calculations are performed using software. The formula above can be implemented in Excel to create a 95% prediction interval for the forecast for monthly revenue when X equals 80, 000 is spent on monthly advertising. Figure 14. 10 shows the detailed calculations in Excel to arrive at a 95% prediction interval of 13,270.95, 15,370. 9 for the monthly revenue. The commands refer to the Excel data table shown in Figure 14. 9. A screenshot of a spreadsheet that shows the calculations for the upper 15,370, 93 and lower 13,270. 946, bound of a 95% prediction level. It shows the measurement in column E, symbol in column F, value in column G, and the Excel command or formula for 9 statistical calculation inputs in column H. The measurements are sample size, degrees of freedom, X-bar, standard error, squared deviations of X, value of X for predictor, forecasted value of Y, value of t-distribution, and margin of error. The Excel commands used to determine the upper and lower bound are as follows. Please note any references to column C or B refer to data presented in Figure 14. 9. The Excel command to calculate the sample size is equals count open parenthesis C2:C13 close parenthesis. The value of this is 12. The Excel command to determine the degrees of freedom is equals G3 minus 2. The value of this is 10. The Excel command to calculate the X-bar is equals average open parenthesis B2 colon B13 close parenthesis. The value of this is 103. 580 3,333. The Excel command to calculate the standard error is equals STEYX open parenthesis C2 colon C13, comma B2 colon B13 close parenthesis. The value of this is 443. 92,908. The Excel command to calculate the squared deviations of x is equals DEV SQ open parenthesis B2 colon B13 close parenthesis. The value of this is 13,054. 917. The Excel command to determine the value of x for prediction is NA. The value of this is 80. The Excel command to determine the forecasted value of y is equals forecast open parenthesis 80, C2 colon C13, comma B2 colon B13 close parenthesis. The value of this is 14,320. 520. The Excel command to determine the value of t distribution is equals ABS open parenthesis T dot INV open parenthesis 0. 25, G 4 close parenthesis close parenthesis. The value of this is 222,813,885. The Excel command to determine the margin of error is equals G10 asterisk G6 asterisk SQRT open parenthesis 1 plus 1 G3 plus open parenthesis G8 minus G5 close parenthesis caret 2 G7 close parenthesis. The value of this is 1049. 573. The Excel command to determine the lower bound is equals G9 minus G11. The value of this is 13,270. 946. The Excel command to determine the upper bound is equals G9 plus G11. The value of this is 15,370. 93. Figure 14. 10 calculations for 95% prediction interval for monthly revenue. This prediction interval can be interpreted as follows. There is 95% confidence that when the amount spent on monthly advertising is $80,000, the corresponding monthly revenue will be between $13,270, 95 and $15,370, $9. Various computer regression software packages provide programs within the regression functions to provide answers to inquiries of estimated predicted values of y given various values chosen for the x variable, s. For example, the statistical program R provides these prediction intervals directly. It is important to know just which interval is being tested in the computer package, because the difference in the size of the standard deviations will change the size of the interval estimated. This is shown in Figure 14. 11. A bell curve diagram that shows that the prediction interval is higher than the confidence interval at a 95% confidence level. Figure 14. 11 prediction and confidence intervals for regression equation at 95% confidence level. Figure 14. 11 shows visually the difference the standard deviation makes in the size of the estimated intervals. The confidence interval, measuring the expected value of the dependent variable, is smaller than the prediction interval for the same level of confidence. The expected value method assumes that the experiment is conducted multiple times rather than just once, as in the other method. The logic here is similar, although not identical, to that discussed when developing the relationship between the sample size and the confidence interval using the central limit theorem. There, as the number of experiments increased, the distribution narrowed, and the confidence interval became tighter around the expected value of the mean. It is also important to note that the intervals around a point estimate are highly dependent upon the range of data used to estimate the equation, regardless of which approach is being used for prediction. Remember that all regression equations go through the point of means. That is, the mean value of y and the mean values of all independent variables in the equation. As the value of x gets further and further from the x, y point corresponding to the mean value of x and the mean value of y, the width of the estimated interval around the point estimate increases. Choosing values of x beyond the range of the data used to estimate the equation poses an even greater danger of creating estimates with little use, very large intervals, and risk of error. Figure 14.12 shows this relationship. The line diagram shows the confidence interval for an individual value of x, xb, at 95% confidence level. It is observed that the value chosen to predict y, xb in the graph, is further from the central weight of the data. The interval expands in width, even while holding constant the level of confidence. Figure 14.12 confidence interval for an individual value of x, letter 1d47f, letter 1d429, at 95% confidence level. Figure 14.12 demonstrates the concern for the quality of the estimated interval, whether it is a prediction interval or a confidence interval. As the value chosen to predict y, letter 1d44b, letter 1d45d, in the graph is further from the central weight of the data, x, we see the interval expand in width, even while holding constant the level of confidence. This shows that the precision of any estimate will diminish as one tries to predict beyond the largest weight of the data, and most certainly will degrade rapidly for predictions beyond the range of the data. Unfortunately, this is just where most predictions are desired. They can be made, but the width of the confidence interval may be so large as to render the prediction useless. Learning outcomes. By the end of this section, you will be able to generate correlation coefficients using the R statistical tool, generate linear regression models using the R statistical tool, generate correlation coefficients using the R statistical tool. R is an open-source statistical analysis tool that is widely used in the finance industry. R is available as a free program and provides an integrated suite of functions for data analysis, graphing, and statistical programming. R provides many functions and capabilities for regression analysis. Recall that most calculations in R are handled via functions. The typical method for using functions in statistical applications is to first create a vector of data values. There are several ways to create vectors in R. For example, the C function is often used to combine values into a vector. For example, this R command will generate a vector called salaries, containing the data values 40,000, 50,000, 75,000, and 92,000. Salaries C, 40,000, 50,000, 75,000, 92,000. To calculate the correlation coefficient R, we use the R command called cor. As an example, consider the data set in Table 14.8, which tracks the return on the S&P 500 versus return on Coca-Cola stock for a 7-month time period. Month, S&P 500. Monthly, return percent. Coca-Cola. Monthly, return percent. Jan 8.6, Feb 1.0, Mars 0, April 2.1, May -3, Jun 7.8, Jul 4.2. Table 14.8 monthly returns of Coca-Cola stock versus monthly returns for the S&P 500. Create two vectors in R, one vector for the S&P 500 returns and a second vector for Coca-Cola returns. SB 500C 8102-374. Coca-Cola C 60-2 1-182. The R command called cor returns the correlation coefficient for the X data vector and Y data vector. Cor SB 500 Coca-Cola. Generate linear regression models using the R statistical tool. To create a linear model in R, assuming the correlation is significant, the command lm for linear model will provide the slope and y-intercept for the linear regression equation. The format of the R command is lm dependent variable vector, independent variable vector. Notice the use of the tilde symbol as the separator between the dependent variable vector and the independent variable vector. We use the returns on Coca-Cola stock as the dependent variable and the returns on the S&P 500 as the independent variable. And thus the R command would be lm Coca-Cola SB 500. Col lm formula equals Coca-Cola SP 500. Coefficients intercept SB 500 34530 8641. The R output provides the value of the y-intercept as -0 3453 and the value of the slope as 0 8641. Based on this, the linear model would be circumflex y equals letter 1d44e plus letter 1d44f, letter 1d465. Circumflex y equals minus 0, 3453 plus 0, 8640, 1 letter 1d465. 1421, where x represents the value of S and P 500 return, and y represents the value of Coca-Cola stock return. The results can also be saved as a formula and called model using the following R command. To obtain more detailed results for the linear regression, the summary command can be used as follows. Model LM Coca-Cola SB 500. Summary model. Call LM formula equals Coca-Cola SP 500. Residuals 1, 2, 3, 4, 5, 6, 7. 5672 minus 0. 5188 minus 1. 6547 minus 0. 3828 193 75 2 2969 minus 1. 1109. Coefficients. Estimate SDD. Error t-value PRT. Intercept 34530. 7836 minus 0. 441 0. 67,783. SB 500 0. 8641 0. 1734 4. 984 0. 416. Signif codes. Asterisk 01 asterisk asterisk 01 asterisk 05 011. Residual standard error 1. 658 on 5 degrees of freedom. Multiple R squared. 08325 adjusted R squared. 07989. F statistic 24. 84 on 1 and 5 DF p-value 0. 4161. In this output, the y-intercept and slope is given, as well as the residuals for each x value. The output includes additional statistical details regarding the regression analysis. Predicted values and prediction intervals can also be generated within R. First, we can create a structure in R called a data frame to hold the values of the independent variable for which we want to generate a prediction. For example, we would like to generate the predicted return for Coca-Cola stock, given that the return for the S and P 500 is 6. We use the R command called predict. To generate a prediction for the linear regression equation called model, using the data frame where the value of the S and P 500 is 6, the R commands will be a data frame SB 500 equals 6, predict model A. 1. 4, 839,062. The output from the predict command indicates that the predicted return for Coca-Cola stock will be 4. 8% when the return for the S and P 500 is 6%. We can extend this analysis to generate a 95% prediction interval for this result by using the following R command, which adds an option to the predict command to generate a prediction interval. Predict model at interval equals predict. Fit LWR upper. 1, 4, 839,062 0. 5,417,466 9. 62,395. Thus, the 95% prediction interval for Coca-Cola return is 0.5%, 962%, when the return for the S and P 500 is 6%.